Hello everybody. Today we're going to be looking at the second section of chapter 14, which is about properties of fluids. Now we've already looked at states of matter, solids, liquids, and gases. We're going to focus on properties of fluids. But now, what exactly is a fluid? Well, a fluid is a substance that can flow. It's particles, whether they're atoms, ions, or molecules. They can flow against each other or even separate, and they can take the shape of whatever container they're in. A solid cannot do this because its particles are stuck together in a rigid pattern. So fluids can be liquids or they can be gases. Both exhibit fluidic properties. Now, the main idea that we're going to be looking at in this section is that fluids can flow, as we just said, and they can also do one more thing. They can exert forces on objects. In fact, that's a lot of what we're going to be talking about today, is the forces that fluids, like liquids and gases, can exert on other objects. For example, have you ever wondered why a huge metal ship will float on water? Because, as most of you know, you get in a swimming pool and you drop a penny, it sinks. A penny is made of metal. In fact, anything you drop that's made of metal will sink to the bottom of the pool. So why don't these huge metal ships also sink? Well, let's take a look at what we already know about objects versus fluids. If you have an object that is less dense than a fluid like water, water has a specific density, and if an object has a density less than that, the object will float. We also know that objects that are more dense than water, like a penny, will actually sink. Let's look at some examples so we remember. If an object floats, it's probably made of wood or maybe styrofoam, or maybe some sort of plastic, or maybe even some type of rubber. Anything that is less dense than water will float. Now, if it's more dense, it will sink, and some substances could be concrete, glass, it'll sink. Rock or stone sinks. Metals sink. So, how in the world do those huge ships float? Well, it has a lot to do with a specific force that fluids exert on objects, and that is buoyant force. Buoyancy or buoyant force, we're going to use an F for force and a B for buoyancy if we have to symbolize it, if that's okay. Buoyancy or buoyant force is the ability of a fluid or gas to exert an upward force on an object that's immersed in it. Let's look at some examples. Look at this picture. You have two objects that are being immersed in a liquid, and I'm going to assume it's water because it's blue colored. And the buoyant force in this first one is a bigger arrow than the weight of the object. This is the weight of the object. And if you remember, the weight is the Earth's gravity pulling on it. Okay? So if the weight of the object is less than the buoyant force, then the object will float. But if the buoyant force is smaller than the weight of the object, GHT, make sure I'm spelling it right, then the object will sink because the bigger force is pushing down. So, let's make sure we have this correct. When the buoyant force is greater than the weight of the object, it will float. But when the buoyant force is less than the weight of the object's going to sink. Okay? Now, most people back in the ancient days understood that liquids exert a force on objects and it makes them either float or sink. It was, however, a Greek mathematician named Archimedes who first figured out something very important about this buoyant force. Now, we've talked about Archimedes before. Now, if you'll remember, Archimedes was responsible for figuring out how to find the volume of irregularly shaped objects using water displacement. So he figured out the water displacement method for finding volume. And of course, that's usually used for irregularly shaped objects that you don't have a mathematical formula to use, like a cube, which would be length times width times height. So you don't have a mathematical formula for oddly shaped objects. You have to use the water displacement method. If you remember, you put an amount of water in a measuring device like a graduated cylinder or a beaker. You measure the level of the water. You put your object in. You measure the new level of the water, and you subtract the two measurements. The volume of the displaced water is the volume of the object. Archimedes understood that, but he determined something else about buoyant force. Here's what he said, and today we call it Archimedes' principle. Now, in some older texts, you might actually see it called the law of buoyancy, but basically, most everybody calls it Archimedes' principle. Here's what he said. He said that the buoyant force, this force exerted by the fluid upward on the object, that it is equal to the weight of the fluid, in this case water, that is displaced by the object. Okay? So he said the buoyant force is equal to the weight of the displaced fluid, not the weight of the object, but the weight of the fluid displaced by the object. You know, that difference, that volume that the water or the fluid rises when you put something in it. Whatever the weight of that fluid is, it's equal to the buoyant force it exerts on the object. Okay? Now, there are 3 different ways we can look at buoyancy. First is negative buoyancy, and this is the object that sinks to the bottom, because here the buoyant force or weight of displaced fluid, and we're going to say fluid here instead of water because it could be any liquid or gas. The buoyant force or weight of the displaced fluid is less than the weight of the object. This means that the buoyant force isn't big enough to support the weight of the object, so it sinks. All right? And I'm going to underline less than in red because that's very important. Then there's positive buoyancy. Now, positive buoyancy takes place when the weight of the displaced fluid is much greater than the weight of the object. In other words, the weight of the displaced fluid, the buoyant force. And you know what we're going to do here? We're going to put this right here. The weight of the fluid. Okay, the weight of the fluid displaced. That's FL for fluid. That's not an H. Okay? Sorry about the clock, guys. We'll let it go here for a moment. It's 8 o'clock. We got to hang on for 6 more bongs. 4, 3, 2, 1. That's it. Okay. So, when the weight of the fluid is greater than the weight of the object, all right, then it's going to float. So when the buoyant force or weight of the displaced fluid is greater than the weight of the object, it floats. The object will float. Okay, and I'm going to underline greater than right there. Now, let's talk about the last one, neutral buoyancy. And remember, the buoyant force equals the weight of the displaced fluid. Okay? So, in neutral buoyancy, the object neither floats above the surface nor does it sink to the bottom. Because the buoyant force is exactly equal to the weight of the object, then the object will be submerged but not sink. It will be sort of suspended in the water or the fluid. So here we're going to write the buoyant force, oops, forgot the T. The buoyant force or weight of displaced fluid is equal to the weight of the object. Then it is suspended in the fluid. It's submerged and suspended, okay? It's just kind of floating at some level right there, okay? So the buoyant force, when it's equal to the weight of the object, then the object will be suspended in the fluid. It won't be floating above the surface because that force is not, it's not big enough to push it up, but it will keep it from sinking to the bottom. It will balance it. So it won't go up or down. It'll stay right there. Now, none of this still explains why those huge, gigantic metal ships float on the water instead of sinking. Well, we're getting to that right now. I want you to notice that all of the objects that we're looking at right here, these objects are all solids. And by that, I mean that they are solid all the way through. No air pockets. That's what has a lot to do with the big ships floating on the water. Let's take a look. If you change the page, look right here. You have a great big cruise ship or any great big ship made of metal, but you've got to remember, it's not solid metal. There's lots of air pockets in here, in the hold, in the cabins, in the open public areas. There's lots of air. And that makes the volume of the ship very large. In fact, large enough that the water it displaces weighs enough to produce a buoyant force that will balance the weight of the boat and it will float. Okay? If we took all that metal and melted it down into one lump, the lump would sink because it is denser than the water, and the buoyant force that would be exerted would be small because all of it collapsed together is a small volume. So the water displaced is small, which means it has a small weight and therefore a small buoyant force. It's not enough for the weight of the metal when it's solid all the way through. But here you've got all this air mixed in. So that makes the volume big, which means the volume of water displaced is big, and therefore the weight of that displaced water is also big enough to support the weight of the boat and make it float. All right, so over here I'm going to underline, okay? The ship will displace more water, and more volume displaced means a greater buoyant force exerted upward on the ship, okay? And that's why it floats. Now there is another way to look at it, and that's in terms of density. You know, we said objects that are less dense than water will float. Well, how is the density less here? Well, you have to average it, all the air and all the metal. If you average the density of that huge volume, it's actually less than water. So the boat floats. So that's two ways we could look at it. We can look at it in terms of density and the average density of the boat plus air, which is less than that of water. Or we can look at it in terms of Archimedes' principle, the fact that that huge ship displaces a huge amount of water, enough water that its buoyant force will support the weight of the boat and make it float. Now, that's pretty cool. Okay, tomorrow you're going to have a discussion on Archimedes' principle, and there's a neat video for you to watch. I kind of like this video because I learned something interesting. I had always thought that Archimedes jumped out of his tub and ran naked through the town yelling, "Eureka!" because he had figured out how to determine if the king's crown was made of pure gold. Well, I found out from this video that that's actually incorrect. So, take a look at it. See what you think. Bye-bye.